Hi everyone, this is Group 15 with myself, Jared, Ethan, and Leon, and our problem was a flour mill filtration problem. So specifically, our problem outline was a flour mill desires to install our particulate matter control equipment to remove 90% of its emissions. The flour has a geometric mass mean diameter of 32 microns, a geometric standard deviation of 2.5 microns. It has a particle density of 1400 kilograms per cubic meter and a volumetric flow rate of 500 meters cubed per minute. Finally, the average flour concentration was 500 milligrams per cubic meter. And so a few reasons why our control technology was needed. The main one is for dust control. I'll get into that a little bit more detailed later, but dust can influence your worker health, worker safety, and then it can also have some explosion hazards, so that's all covered under dust control. And then finally, it can clog up your ventilation system. So normal HVAC systems aren't designed to deal with the amount of dust coming in that would be produced from this flour mill, and they can get clogged up, they can get ruined essentially, and have to be totally reinstalled. So taking a little deeper dive onto worker health effects, we found several articles on some specific health effects, and one of them being from WorkSafe BC. It says that flour dust is a hazardous substance, and workers in baking-related jobs or like a flour mill could become affected by it. So specifically, it can irritate the respiratory tract and lead to some occupational asthma, and it actually has its own name called baker's asthma. And these health problems can develop over many years. It says 30 here, but you can start experiencing them pretty quickly. And then it also says flour dust can cause explosions, which we'll get into in the next slide. So some specific short-term effects, this would be like almost instant exposure, would be runny nose and eyes, wheezing, sneezing, coughing, and shortness of breath, all of course related to the respiratory tract. And then as we mentioned earlier, some long-term effects would be occupational asthma or baker's asthma. All right, some of the worst things that could happen could be a flour mill explosion. So also from the WorkSafe article, it says like any other organic matter, flour is combustible if it's ground finely enough, and it can explode pretty easily if the concentration is high enough. And this actually has happened several times. There were some recent cases, but one of the worst cases is prior to any sort of filtration. This happened on May 2nd, 1978 in a flour mill in Minnesota. It was the largest flour mill in the US at the time. And what happened was the flour from the mill built up too much inside, and some spark caused it to explode. The explosion killed 18 people in total, and it absolutely decimated the surrounding area. There were many fires in the surrounding area. Several other mills managed to burn down as well. And then, of course, this event led to reforms in the milling industry, and ventilation systems like our control technology were developed. And here are just a few pictures from that event. So on the left, you can see an illustration of what the factory would have looked like mid-explosion. As you can see, the plume of the explosion is absolutely massive. It dwarfs the building underneath it. And then to the right is an actual picture of the aftermath of the building. So you can see the roof is completely blown off. All the windows are gone. There's debris everywhere on the outside. And then if you look further, you can see that all of the surrounding area is also destroyed. So as I mentioned earlier, there were 18 people killed. So there were 14 people killed inside the mill, and then 4 other mill workers killed from the resulting fires that were outside the mill. And there were at least 16 injured, if not more. So that leads us into the stakeholders who will benefit. So the first stakeholder that would benefit is the flour mill company. They obviously don't want damage to their facilities, catastrophic explosions, worker health effects, or any EPA fines or regulations to come down on them. The second stakeholders who would benefit were mentioned earlier with the workers. Obviously, they don't want any health effects for them either. They don't want any long-term or short-term health effects while they're working, as that could affect their work and thus their pay. Third is the local residents around the flour mill. Obviously, they don't want any flour getting inside their homes, inside their lungs, inside any of their pets, on any of their yards or anything like that. So it would be a big benefit for them as well. And finally, we have two that are essentially combined into one, the local wildlife and the local ecosystems. So the local wildlife could be affected if the flour mill is just discharging at their current rate without any kind of regulations or any kind of not remediation, any kind of particulate matter control like we're suggesting here. And it can have similar health effects to a human, as in long-term asthma, and then the short-term effects of runny eyes, wheezing, coughing, and just general respiratory issues.
All right, so we found 3 control technologies and considered applying each of them to the flour mill. First, we did the baghouse filter, which is a very simple filtration system that pushes dirty air up through the bottom of the system, where it goes through filters, which are adjustable based on the target contaminant. The clean air moves through the filters while the contaminants are left behind, but baghouse filters can be self-cleaning, as certain ones blast air down the baghouse that backwashes the filter and cleans out all the built-up particles. These particles then drop down and are collected in a hopper at the bottom of the system. The baghouse filter is very versatile, having extremely high removal efficiencies, up to around 99% in some instances, for particles from submicrons to hundreds of microns in diameter. This system is used in a large range of industrial applications, such as the production of chemicals and pharmaceuticals. I personally have experience with this technology, as 2 summers ago I did an internship at a plastic factory. The company makes acrylic plastic primarily in sheets, but they also break down sheets to make plastic filaments, and that flings small plastic chips in the air, and baghouse filters are all over the roof and pick up a good proportion of the plastic floating in the air. And then the next one is the electrostatic precipitator, which is a simple system that uses a group of electrodes to give particles in the air a slight charge. The air with charged particles then moves through the center of the precipitator, where collection plates are rotating. Charged particles stick to these collection plates due to electrostatic forces, and then gravity draws the particles down to the bottom, where they're collected by a hopper again. This is another air quality system with high removal efficiency for many particles, including the target 32 micron flour. It also prevents bacterial buildup, unlike the baghouse filter, where the filter needs to be cleaned routinely. This bacteria prevention can be advantageous for food-related air quality problems, yet the electrostatic precipitator is most commonly used in petroleum refineries and coal-fired power plants, as the many volatile organic compounds emitted from those places need to be removed from the air. And then our last one is the cyclone dust separator, which does exactly what its name says. It creates a cyclone within the interior that utilizes centrifuge forces to remove particles or even liquids. Airflow for the cyclone separator begins at the top of the cone and moves downward at high speeds, which causes higher density particles to be removed from the air. These particles hit the outer shell of the system and then fall into a collector at the bottom, allowing for clean air to flow out of the system. Particles above 5 microns are able to be removed with high efficiency, and particles 20 microns or greater are able to be removed with efficiency still at or above 90%. The cyclone dust separator is versatile, and essentially every parameter can be adjusted depending on particle size and the scope of removal in order to more efficiently remove specific suspended material. These systems have a multitude of applications, including use in personal workshops for the removal of sawdust from the air, or even in industrial settings like, again, chemical plants or in paper production. And I know there's a smaller cyclone dust separator here at OSU in the Smith Lab basement. The room down there is the engineering education department's workshop, where there's a lot of woodworking. So the cyclone dust separator keeps the room clean by removing sawdust.
All right, so for our buffer control technology, we chose to use the cyclone dust separator, mainly because just to simplify the efficiencies. Instead of using bag filter that has a very high efficiency, we're going with something that's going to be more efficient, and actually you'll see the calculations later, but we still got a very high efficiency with the cyclone. So it removes about 90% efficiency when particles around 15 to 20 microns, and we actually found about 99% in our calculations that you'll see later on. And these are also with the particles being in the problem 32 micrometers or microns. And there's also a very low maintenance cost. There's not really much to clean, as everything's kind of in pieces, and there shouldn't really be too much buildup of particles or anything. Particles that hit the cyclone will end up at the bottom and should be able to be collected very easily. It's also very durable, so kind of how I talked about the pieces, there's also ability for it to not break apart as easily if there's moving parts. And we really just have a couple pieces of the funnel that are the only real issue you might have is with abrasive forces. And you can actually add another flow into the cyclone that allows for a decrease of the amount of particles hitting the cone, which would lead to less abrasive forces and lead for a longer lifetime of the cone itself. It's also the cheapest option out of the three. I calculated it to be about $2,500 with all the parts included in it for about the sizing that we're going to use. So yeah, compared to the other two options, it's the most cheapest. All right, and then we have design equation and parameters. So D is kind of the barrel diameter that we're going to use. We also use this table to multiply what we get for the barrel diameter to get the other units or the other lengths and widths and dimensions of our cyclone. So the barrel diameter we calculated using the volumetric flow rate, the inlet velocity that we got from the problem, and it came out to about 2.01.
Using the calculations that we have above, motherfucker, whatever. Okay. So using the equations that we had above to get conversions, we end up with these dimensions as listed here. 2.108 meters for the barrel diameter, 1.054 for the inlet height, 0.527 meters for the inlet width, a gas exit diameter of 1.054 meters, vortex finger length of 1.318 meters, body length of 4.216 meters, cone length of 4.216 meters as well, and a Dutch outlet diameter of 0.527 meters. We think these are generally acceptable both because they fit the conversions in the equation that we found earlier, so we know that they're correct, but also this entire operation should fit roughly in the size of a cone that has less than 30 cubic meters overall. So we think that it'll be reasonable to install and operate, won't take up too much space within the flour mill's operation. Moving into the calculation for the efficiency. So first, we have this equation here, which represents the particle collection probability distribution, given a certain D50 or the 50-50% probability diameter of a particle of whether or not it's going to get collected. If we set the D50 equal to this equation for the cut point and use this as the lower bound for the integral above for the particle collection probability distribution, we actually end up with the overall efficiency. So calculating the D50 with the value below, we end up with a diameter of 1.947 microns. Plugging that into the probability distribution to find the overall efficiency, we end up with an overall efficiency of 99.887%, which exceeds the 90% efficiency that we were trying to aim for. So as an overall conclusion, we think that this is an effective solution because the dimensions take up reasonable space. It'll be reasonable to install and operate as well for the flour mill. It's easy to clean because it's all different compartments and pieces. So being easy to clean means that we won't have microbial growth and it'll be safe for use in the food production of flour, and the efficiency that we're producing on top of that exceeds the stakeholder request of 90%. Here are our citations. Thank you very much for your time.